Welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also do see and appreciate the beauty in the simpler problems. So today, we've pretty much uh, gone through the MIT Integration B of 2023, 2022, and now we step back to MIT 2020 Integration B. And we'll be focused mainly on the qualifying exam. There were 20 questions. So today we do question 1 to question 10. And then maybe in our next session, we'll handle question 11 to 20. So there were 10 questions, as I mentioned. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We're going to handle 10 questions today, and then next session we handle the remaining 10. So before I jump into the solution, I'd like to just thank our subscribers. Thank you so much for the overwhelming support that you continue to show us. It's with your support that we get the motivation to come back here once again and continue sharing the solutions to some of these problems with you. To our first-time visitors, the main motivation for our channel is that we go out there, look at very hard mathematical problems, and then we come back here and share the solutions with you. For returning visitors who haven't subscribed, we do really encourage you to subscribe to our channel because we do enjoy doing this and we would like your support going forward. So let's go into question number 1. So question 1 is the integral, an indefinite integral of log, a natural logarithm of 2x over x times natural logarithm of x. So one thing that I would do here is just use the rules of logarithm and see this is the product of 2 and x. So when you have product of two numbers, you just add the independent logarithm of those numbers. So we have the integral of log 2 plus log x over x log x, which could also be handled a little bit differently. So we could separate log 2x over x log x and log x over x log x. So you see this log x would this would cancel. So this and this would cancel. And so you're left with just x here. But looking at what we have in the denominator here, there are a couple of things that we can do to solve that. If you assume u to be log of log x, and then e to the power u is equals to log x by taking e to the power of the left and the right hand side respectively. This means that e to the power u du dx is 1 over x. And so du dx is 1 over x times e to the power u, and we know e to the power u to be log x. And so we get du dx being equal to 1 over x times log x. So that means that this 1, removing this constant and having 1 over x log x, this is the derivative of log x. So we can then quickly just say this is the same as log 2 times log x when integrated plus 1 over x remaining from the division of log x here. We'll have the integral being log x and plus integration constant. So that is the answer for this problem. Then problem number 2 is the definite integral from 0 to infinity of 1 over e to the power x plus 1. What I would do here, I would just say let u be equal to e to the power x, and therefore du dx is equals to e to the power x. And so du over e to the power x is equals to dx, and we know u to be equal to e to the power x, and so that means that du over u is the same as dx. And so also the boundaries. So when x equals to 0, that means that e to the u is equals to e to the power 0, which is 1. And then when x equals to infinity, that means that e to the power infinity is infinity, so u is equals to infinity. And so now integral from x equals to 0 to infinity of 1 over e to the power x plus 1 dx is the same as the integral from u is equals to 1 to u is equal to infinity of 1 over u plus 1 times du over u. And so we can now create, we can create we missed the du here. We can create a partial fraction. This here is the same as 1 over u minus 1 over u plus 1. And so the integral here is log u minus log u plus 1 with the necessary limits applied. And so this is the same as with the upper limit as u tends to infinity. This expression is the same as log u over u plus 1. So as u tends to infinity of log u plus log u over u plus 1 means that this is the same as u, this is the same as 1 over 1 plus 1 over u. So when u tends to infinity, this expression tends to 1, and so this tends to 0. And so, and then minus the lower limit when u is equals to 1, this means that this is 1 over u 1 plus 1. So this is 1 over 2, and that means that is negative log a half, and taking the negative 1 here up, that means that it becomes 2. So the answer really is log 2. This is our answer. Problem number 3, which is the integral from x equals to e to e to the power e. X is equals to e to the power e of log x times log x over x. How I would first begin by solving this is by letting u be equal to log x, such that du dx is 1 over x, and therefore x du is equals to dx, and we know x to be e to the power u, so e to the power u du is equals to dx. And when x equals to e, that means log e is equals to 1. And when x equals to e to the power u, that means that u is equals to log e to the power e. Take e as to the constant location here, times log e. So this is times 1, which is 1. And so the integral from x equals to e x equals to e to the power e of log x times log x over x is equals to the integral with u being from u equals to 1 to u equals to e of u times log u over e to the power u times eu du. So you see, this would cancel out, and so we are left with the product of u log u. And so what we can do here is assuming that this here u is the same as dv and log u is the same as u. So using integration by parts, u v is the same as the integral of dv is u squared over 2 log u, and with the necessary limits. And then here we have now du times v, which is u squared times the derivative of log u, which is 1 over u. So this cancels with one of the powers here. So having substituted the limits here, we have e squared over 2 log e minus e minus, 1 squared over 2 log 1. This tends to 0. And so we are left with e squared over 2 log e is the same as 1. And so we have e squared over 2 minus, here we have the integral being u squared over 4 with the necessary limits. So we have e squared over 2 minus e squared over 4 minus a quarter. So e squared over 2 minus e squared over 4 is e squared over 4, and negative and negative here, this becomes positive. So we have a quarter of e squared plus 1. And then we have an integration constant here applied appropriately. So that's number 3. Number 4, we have the integral from x equals to 0 to 1 of log 1 plus x over 1 minus x. So we can use the rule of logarithm. When you have a division under the log function, this is the same as the subtraction of the independent logs of those numerator and denominator values respectively. And so as we can see here, we can assume that we have a hidden dv, and this is u. So using integration by parts, uv would be x log 1 plus x minus x in the numerator, or x times the derivative of log 1 plus x is 1 over x. So multiply that together. And then we have the log of 1 minus x. We assume that dv is x minus 1, and such that uv is x minus 1 times log 1 minus x minus the derivative of log 1 minus x is definitely negative 1 over 1 minus x times 1. And so the negative, this becomes positive. So we have applied the limits 0 and 1 here. And as you can see in this first instance, when x is equals to 1, this means it's 1 log 1 plus 1, which is 1 times log 2. When x equals to 0, 0 times log 1 plus 0 is log 1. So log 1 is 0, and this is 0. So we have 0 there. And so out of this, we have log 2. So this is log 2 here. And here we could divide it the same as 1 minus 1 over 1 plus x integral. And here 1 minus 1 is 0 times log 1 minus, so this is infinity, but this is 0 on the upper side, and when x is equal to 0, is negative 1 times log 1. Log 1 is 0, so this entire thing goes to 0, and then we're left with the integral of this part here. So we say this is log 2, and then we have 1 minus 1 over 1 plus x. And this, as we say, this would tend to 0. And this flipped around where the sign multiplied by negative 1, this becomes 1 minus x. And so the numerator and denominator become equal. So we have only 1 left here. So as you can see, since this is the integral of 1, negative times this negative is positive, so this would cancel with this part here, and so we have log 2 minus the integral of 1 over 1 plus x. Let's see here with the limits applied, this tends to 0, right? And this, as I said, would cancel out because this is 1 and this is 1. And so the final answer is really log 2 here. Okay. Problem number 5 is 1 over x squared plus x minus 1 squared integral. So we can expand the denominator. So we have x plus x squared minus 2x plus 1. So this becomes 1 over 2x squared minus 2x plus 1 divided through by 2. So we have 1 over x squared minus x plus a half. And so this is the same as x minus a half squared minus a quarter. And then we add the half. This is the integral of 1 over x minus a half squared plus a quarter. We can substitute and say let x minus 1 be equal to a half tan theta. And so that means that dx d theta is equal to a half sec squared theta. And so dx is the same as half sec squared theta d theta. And so applying those, the substitution appropriately, here we have 1 over quarter tan squared theta plus a quarter in the denominator, and the times 1/2 sec squared theta d theta. And we're pulling a quarter out and proceeding appropriately. This becomes 4 because the reciprocal of a quarter is 4. And so we have tan squared theta plus 1 times a half sec squared theta. Tan squared theta plus 1 is the same as sec squared theta. So the half here could cancel with 2. So you're left with the 2 here. And so we have 2 times sec squared theta over sec squared theta. So we have the integral of d theta, the integral of 1, sorry. So the answer is really 2 theta plus constant c. But from the initial substitution, we said x minus half is equals to a half tan theta. So that means that when we multiply both sides by 2, we have 2x minus 1 is equals to tan theta. And therefore, theta is the same as the arctangent of 2x minus 1. So the integral here is the same as twice times theta, and our theta is arctangent of 2x minus 1. So it will be now 2 times arctangent of 2x minus 1 plus the integration constant c. And that's the answer. Number 6, the integral of square root of x times square root of x times, nested square root of x times nested square root of x and so on. So if we let y be equal to these complicated nested roots, y squared is the same as x times the same number because this is all tending to infinity. And so x squared is equals to x times y because this is the same as y. And what you see here is that in order to obtain, or in order for this to hold, then y has to be x. And so our integral, this is the same as the integral of x dx. And so the answer is x squared over 2 plus c. Number 7 is our next problem. Sine to the power 4x times cosine to the power 4x times cosine x plus sine x times in bracket cosine x minus sine x. This is the product of the sum and the difference of the same two numbers. So that means that we have sine to the power 4x cosine to the power 4x cosine squared minus sine squared x. And so when you multiply that through, you have sine to the power 4 x cosine to the power 6x minus sine to the power 6x cosine to the power 4x. So this is the same as sine to the power 4x times cosine x times cosine to the power 5x minus sine to the power 5x times sine x times cosine to the power 4x. And you can see here, this is the same as the derivative of a fifth times sine to the power 5x times this cosine 5x. And this here is the same as, including this sign here, a fifth times this sine to the power 5x times the derivative of cosine to the power 5x. Now, since you can see we have cosine to the power 5x here, and we have cosine to the power 5x here. And then we have sine to the power 5x here, and then we have sine to the power 5x here, and the constant here remains. This is the same as the differentiation of a product. And so the same as a fifth times the derivative of sine to the power 5x and cosine to the power 5x. And so the integral of a derivative is therefore just that number. And so we have a fifth sine to the power 5x cosine to the power 5x plus the integration constant as our answer. Problem 8 is the natural logarithm of x squared plus 1 what we could do is we could use integration by parts, and assuming that in place of 1 here, we have a dv. And so v is x. And so if this is u log x squared plus 1, so uv is x plus log squared x plus 1 minus, since v is x, and so du is 2x over x squared plus 1. So we have x times log x squared plus 1 minus 2, pulling 2 out, x squared plus x squared divided by x squared plus 1. And when you divide that, we are left with 1 minus 1 over x squared plus 1. And so integrating everything, we have x log x squared plus 1 minus 2. And integrating 1, we could get x minus 1 over x squared plus 1 integrated. This is a very popular integration problem. This is the same as arctangent of x. And so eventually we have x log x squared plus 1 plus 2 arctangent of x minus 2x plus integration constant. Okay, so this is our answer. And problem 9 is the integral of the cosine to the power 2020 x, the power 2020 of x. And so this cosine, integration of cosine to the power 2020 of x, the same as, I didn't really do anything here, it's so stupid, but it's the same as the integration of cosine to the power 2019 times cosine x. And so using integration by parts, where we assume that this here is the derivative of v, so therefore v is the same as sine x, and then u is cosine the power 2019 of x. So with these limits applied, when sine x is 2, sine of 2 pi is 0, sine of 0 is 0, so everything here tends to 0. And so minus derivative of this du is 2019 times cosine 2018 x times sine x. And so the negative signs would cancel out, and so we're left with 2019 times cosine, the integral of cosine to the power 2018 sine x times sine x. And so if this tends to 0, we have 2019, the integral from 0 to of x is equal to 0 to 2 pi of cosine 2018, cosine to the power 2018 x sine squared x. And this is the same as 1 minus cosine squared x. And so you realize that very soon we have a cyclic or recursive process. And so we have the integral of 2019 times cosine to the power 18x times 1 minus cosine squared x. Multiply that across, we have two separate integrals here. Sorry, this is a negative. So we have the integral of 2019 times the integral of cosine 2018 x minus 2019 times the integral of 2018 x times cosine squared x, which is the same as this. So we can take this entire process to the left-hand side. And so we have 2019 plus 1 is 2020 times this integral being equal to cosine 2019 times the integral of cosine 2018 of x. Now divide both sides by 2020. We have the integral of cosine 2020 from 0 to 2 pi is the same as 2019 over 2020. The integral of x from x equals 0 to 2 pi of cosine 2018 x. Now you can repeat this process once more, and so you do just have a repetition of 2019 over 2020 times 2017 over 2018 times the integral of cosine to the power 2016 of x from x equals 0 to 2 pi. And if you continue this process, you would keep going until you reach a point where we have cosine to the power 0. And then so here, as you can see, we have 2019 times 2017, skipping a number in between. The same thing in the denominator. Right, now to plug in the gaps here, we'll just have to square whatever is in the numerator. But at the end of it all, this is the same as 1. The integral of 1 is x, and with the limits, we get 2 pi, right? So as you can see, we do have a multiplication 2019 times 2018 times 2017, and so on and so on. Let me see where we've so sorry, for now, let's remove it's 2019 times 2017. But this is not there, but we have to skip one number afterwards. We can only now have the numbers between plugged in after we've squared the denominator, so that 2020 up and down, 2018 up and down, and so we're able to get a factorial here in the numerator. As shown there. And then we have twice the factorial from 1010 after pulling the twos out. So dividing every number by 2, we ended up with a factorial from 1010 all the way to 1. And then now we have to pull out 2010 times 1010 times, and then square that, we get to the power 2020. And so you keep continuing. So we have a 2020 factorial here, and in the denominator, since we're squaring this, we have 1010 factorial times 1010 factorial. And then these 2 and one of the 2's cancel out, so we're left with 2019 there in the denominator. So we have 2020 factorial over we have, instead of 1010 factorial, we have 2020 minus 1010 factorial. So we're trying to build what we call a binomial constant there. And so since this 2 has gone now, we have this number being equal to 2020 and 1010 as the constituent of a binomial constant. And sorry, here we just have 1 pi. So the answer, taking this up, is 2 to the power negative 2019 times the binomial constant involving 2020 and 1010 times pi. That's the answer. So the final problem is the integral, indefinite integral of 2x plus 1 over 2x squared plus 2x plus 1. So the problem here is if we multiply it by a half, such that in the numerator we have 4x plus 2 over 2x squared plus 2x plus 1. This clearly shows that in the numerator, this is the same as the derivative of the denominator. And when you have a number whose numerator is the derivative of the denominator, that is the derivative of the log function of that denominator. And so our answer here is half times the log 2x squared plus 2x plus 1 plus the integration constant. So that brings us to the end of the solutions to the 10 problems in the qualifying exam of the 2020 qualifying exam for the integration B. I hope you enjoyed following along. We went a little bit fast, but if you have any questions, please don't hesitate to leave any comments you may have in the comment section. Thank you very much. Until next time, à tout à l'heure, à la prochaine fois.